In the previous lectures, we have introduced the relativistic action for a free particle that looked like this, minus mc ds integrated over the world line of the particle. Now, this is a course on electricity and magnetism, so we're interested in introducing electromagnetic field in the equation. Now, we would like to start with the action and try to figure out what should we add to this relativistic action so that we can obtain the Lorentz force that's acting on the particle. So let's try to invent it from scratch. Whatever we include in the action must be a Lorentz scalar, and it has to be an integral over the world line of the particle. And it has to involve a field with which the particle will interact. So let's try the following addition to the action. Let's try adding a term that looks like a sub alpha dx super alpha. So A alpha will be a 4-vector field that depends on the position in space-time. Now, because it has to be an electromagnetic field, the coupling constant, or the strength of the interaction with the field, has to be given by the particle's charge. So I'm going to put E here, that's the charge of the particle, and for future convenience, I'll add a factor 1 over c, where c is the speed of light. This is a perfectly valid term. Lorentz scalar, it has a proper form for the action. Now, in order to write this in conventional notation, we need to introduce the space-like and time-like components for A alpha. So let's call it phi and A. We will see that this is actually the scalar and vector potentials of electrodynamics. So we'll use phi and A. The covariant components will be phi and minus A. So if we substitute this here, we find, in addition to the first term, plus E over c A dr minus E phi dt. We can easily convert this to an integral over time. So we specialize to a particular reference frame. Now, the first term was found before. It's just minus mc squared times the square root. The term from A dr, we divide and multiply by dt. So here we have A dot dr by dt, but that's v, the velocity of the particle. And then there's a minus E phi from the last term. So all of this is integrated over t. Now, whatever sits in front of dt in the integral for the action, that's the Lagrangian. So first thing, from this Lagrangian, now we use the procedure that we know from classical mechanics. Once we have the action expressed in this form, you just take derivatives of the Lagrangian and you get the canonical momentum and so forth. So the canonical momentum, that's dl by dv. The first term gives us, as before, mv over the square root. The term with a dot v will give us plus E over c a. We can further write this as lowercase p plus E over c a, where lowercase p is just this expression, the same as we had for the free particle. We will call it the kinematic momentum, lowercase p, as opposed to the canonical momentum, capital P, which comes from dl by dv. Okay, so this is the canonical momentum, the next step is to find the Hamiltonian. So to find the Hamiltonian, we must take v dl by dv and subtract L. So if we do that, we obtain mc squared over the square root as before. Now the terms with a dot v will cancel, and what remains is plus E phi. So it looks like the vector potential is not here, but in fact this expression is not in proper form. Here it's expressed in terms of the velocity, but the Hamiltonian must be expressed in terms of the momentum. In order to do that, we can use the following expression. We can write h minus E phi squared equals m squared c to the fourth plus c squared capital P minus E over c a squared. So where does this expression come from? Well, it's just the relation between the kinematic momentum, this quantity here, and the energy of the free particle, which is expressed in terms of the Hamiltonian and the canonical momentum. So take the Hamiltonian and subtract E phi. You get this expression for the energy of a free particle that's on the left, and then capital P minus E over Ca is the kinematic momentum. Using this expression, we can now write the Hamiltonian as square root of m squared c to the fourth plus c squared capital P minus E over Ca squared plus E phi. In the non-relativistic limit, the Lagrangian becomes approximately mv squared over 2 plus E over c a dot v minus E phi. I dropped the rest energy, and the Hamiltonian becomes 1 over 2m canonical momentum minus E over Ca squared plus E phi. Given the Lagrangian, we can now derive the Euler-Lagrange equations, or the equation of motion for the particle. So again, dl by dv, that's kinematic momentum p plus E over Ca. Now, kinematic momentum is just mv over this square root. Now, to write the Euler-Lagrange equation, we also need dl by dr. Now, what depends on r in the Lagrangian? Well, a and phi depend on the coordinates. So a and phi are the field potentials that depend on space and time. So dl by dr is the gradient of a dot v minus E del phi. Now, what should we do with this gradient of a dot v? Now, notice that this derivative, it's a partial derivative. It's a partial derivative in a sense that r dot, or the velocity of the particle, is held constant while we take this derivative. This is how the Euler-Lagrange equations are derived. So here only a is differentiated with r. Now there is a general vector analytic expression which can be used to rewrite the gradient of a product of two vectors. So we can write it as v dot del a plus a dot del v plus a cross curl of v So far I'm just writing an expression that is valid for any vectors a and v. So this is the expression. Now, because the gradient operator actually acts only on a and not on v, we have to drop the terms where del acts on v. So this term should be removed, and this term should be removed. The Euler-Lagrange equation is the full time derivative of dl by dv equals dl by dr. So now we can substitute into this expression. So we'll have d by dt, and here goes the right-hand side from here. So here we have p plus e over c a, and the right-hand side is e over c v dot del a plus e over c v cross curl of a minus e del phi. Now, as you can see on the left-hand side here, we have a full-time derivative of a. Now, where does this full-time derivative come from? Well, there are two contributions to dA by dt. There's the one that comes from a depending on time explicitly, and the part that comes from the fact that the particle is moving and the value of the vector potential at t plus dt is measured at r plus v dt rather than r. So the motion of the particle gives this additional contribution to the full time derivative. Now, if we substitute this full time derivative into the left-hand side here, you see that the term coming from e over c times v dot del a exactly cancels the same term on the right-hand side here. So what remains then is dp by dt. Let's take the partial time derivative to the right. So we have minus e over c dA by dt plus e over c v cross curl of a minus e del phi. So there are two terms here. There's one term that is proportional to the charge, and then some function that includes the derivatives of the scalar and vector potential, and another part that contains a cross product with the velocity. So it is easy to recognize this form as the Lorentz force with the electric and magnetic field that can be written as E equals minus 1 over c dA by dt minus del phi. And then we have the magnetic field, which is curl of A, so that dP by dt, which is the force acting on the particle, is given by E times E plus E over C V cross B. This is the Lorentz force, the conventional Lorentz force from electrodynamics. Notice that the momentum here in dP by dt is the full relativistic momentum. It's not just mv, it's this whole thing. Let's recap what we did so far. So we took our expression for the action, where we had a term corresponding to the free particle depends only on the coordinates of the particle, and added a new term, which we just postulated based on something that obeys Lorentz invariance. We varied this action, and this gave us the Lorentz force. The correct form, which strongly suggests that these components of the four-vector potential are actually the scalar and vector potentials of electrodynamics. So this is quite encouraging. Now let's also notice another feature of this action term that we have introduced that strongly supports the identification of the four potential with the phi and A. Let us now consider another property of this action that we've introduced, the term with the field. Let's see what happens if we take our four potential and we replace it by a different field that differs from A alpha by a gradient of a scalar function. So introduce an arbitrary function f that is differentiable, and then see what happens if we insert this A prime instead of A into the action. Now, if we write it in components, we'll see that this four gradient corresponds to subtracting the time derivative of the function f from the scalar potential and adding the gradient of f to the vector potential. Now, if we substitute this new A prime into the action, it's easy to see that the new action will acquire an extra term which looks like df by dx alpha dx alpha. Now, this integral is nothing other than the integral of a full differential df. Okay? Now, the full differential of df simply gives us f of b minus f of a. Now, this term does not depend on the trajectory of the particle, because the initial and final points, a and b, are fixed. This term here is a constant. It does not depend on anything the particle does between a and b. So, as a result, the equations of motion, or the Euler equation, the Lorentz force that we found, is unchanged by this redefinition of A. We'll get exactly the same motion for the particle if we write the action with A or A prime that is redefined in this way. Now, if you look carefully, you'll recognize that this is nothing other than the gauge transformation. This is the familiar gauge transformation from electrodynamics. So you take a gauge function f and you redefine phi and a, and you get the same fields and the same equation of motion. So here we see how in the action term that we've invented, this gauge symmetry is actually built in. The structure of this action term is gauge invariant to begin with. Now, the drawback of the approach that we used, where we took this action and represented it in terms of the integral of L dt, and then took that Lagrangian and found the equation of motion for the particle, is that the fields, the E and B fields, came out in a way that that is not explicitly covariant. So these are conventional three-dimensional vectors, and it's not clear from here whether they form part of some 4-vector or 4-tensor in the Lorentz invariant covariant notation. So in order to expose that, we need to come back to the action here and then try to vary it like we did before for the free particle, now including the field term, but do it in a fully covariant form. So this is our action. To better keep track of things, let's call this first term S sub p, which would stand for the action for the particles, and the second term as S sub pf for the interaction of particles with the fields. So we have already varied the first term. We know that delta sp is equal to m integral delta x alpha du alpha by ds ds. So we don't need to do this again. So the new thing is the second term. So we need to vary delta, vary SPF. Okay. Now we have a product of two terms there, and they both will contribute to the variation because we vary the world line. That's the dx alpha, but the potential seen by the particle is also varied because it's now sampled at different points in spacetime. So I'm going to have two terms, delta A alpha dx alpha plus A alpha delta dx alpha. So now we're going to do the following. In the first term, delta A alpha. So where does this variation come from? Well, it comes from the fact that x alpha is varied. So A alpha is a function of x alpha. So here we'll have dA sub alpha over dx beta delta x beta. Summation over beta is assumed. Now in the second term, we have delta dx alpha. Now the variation and differentiation are both linear operations. So this is the same thing as d delta x alpha. So I'll insert this directly into the formula. And then, of course, the second term will be integrated by parts. So what have we got? From the integration by parts, there will be a free term, minus e over c, A alpha, delta x alpha, AB. And the free term will go like delta x alpha, d A sub alpha. That's from the second term. And from the first term, we'll have minus dA alpha dx beta delta x beta dx alpha. Now, in the first term, we're going to use that dA sub alpha equals dA sub alpha over dx beta dx beta. So this is analogous to this expression, except that here we have a differential instead of the variation. Now, in addition, we want to take delta x alpha outside of the brackets. Now, in the first term, it comes with the superscript alpha, and here it's beta. We want to have the same index. Now, the indices that repeat, after all, this is all a scalar expression. So indices that repeat are dummy indices, so we can rename them any way we want. So we're going to swap alpha and beta in the second term. Now, we also know that the first term is actually 0 because delta x alpha is fixed at the initial and final points on the trajectory, so the variation delta x alpha vanishes there. So taking everything into account, now we have e over c integral delta x alpha goes outside the brackets. So here we have dA alpha dx beta dx beta. Second term dA beta dx alpha, remember we're interchanging indices, dx beta and delta x alpha goes outside the brackets. All right, so now we also have dx beta that we can take outside of the brackets. So let's do that. And finally, divide and multiply by ds, and then dx beta by ds is just 1 over c u beta. So plug this in. And finally, here we have a second-rank tensor with two covariant indices. So let's denote it f beta alpha, two lowercase indices. So now we can write the equation of motion by using the vanishing of the variation. So we need to collect the two terms, the term with delta SP and delta SPF. When we collect them, delta x alpha is outside of the brackets in both terms. So let's actually write it down. So the full variation of the action, delta S, we have integral from a to b, delta x alpha. Now then there will be a long bracket, and ds is taken outside. So here we have m du alpha by ds. That's from the first term. And from the second term, we have plus e over c squared f beta alpha u beta. The variation has to vanish for the arbitrary delta x alpha, which means the entire bracket here has to vanish identically, which gives us the equation of motion. mc du alpha by ds equals e over c f alpha beta u beta. So here I have interchanged the indices of beta alpha to alpha beta. That changes the sign because the tensor f is anti-symmetric, so I take it to the right with a positive sign. So this is the equation of motion written for u with a covariant index. I can write a similar equation with contravariant indices. That would go mc du alpha by ds equals e over c f alpha beta u sub beta. So this is the equation of motion for a particle in a field. Now this expression is identical to the Lorentz force that we derived before, but here everything is written in a fully covariant form, as we wanted to do. Let us now explore the structure of this second-rank tensor that we obtained, f alpha beta. So we'll just write it out in regular components and see what we've got. So we expect to find the components of the electric and magnetic field embedded into it somehow. So it's an anti-symmetric tensor, which is obvious from the definition. So f alpha beta is negative f beta alpha. All the diagonal elements is 0. So let's first look at component f01. So by definition, it's dA1 by dx naught minus dA naught by dx1. Substituting the definitions, this will be negative dAx by c dt minus d phi by dx. Remember the covariant components of A are phi and minus A. That's why there's a minus sign in the first term. Now, if we come back to the definition of the electric field, this is nothing other than Ex. So as expected, the electric field is an element of that tensor. Now f naught 2 will be similarly EY, and f naught 3 will be EZ. So this is the component where one of the indices is time-like and the other one is space-like. Let's look at the other components where both indices are space-like. So starting with f12, that's dA2 by dx1 minus dA1 by dx2. This is minus day by dx plus dax by dy, which is negative z component of the curl of A. Now the curl of A is by definition the magnetic field, so this is minus bz. The other components are found in a similar way, so we can write the whole tensor f alpha beta. Diagonal elements are 0. F naught 1 is ex here, ey, ez, minus ex, minus ey, minus ez. And then bz is here, that's minus bz. By is here, and bx is here. The contravariant components, if I want a tensor with two contravariant indices, so I need to raise each index. Now whenever I raise the time-like index, nothing happens. Whenever I raise a space-like index, there's a minus sign. So if both indices are time-like or space-like, there's no sign change. If one of them is time-like and the other space-like, there is a sign change. So the components containing the electric field will change sign, but the magnetic field will keep the signs that it had with covariant indices. So the important finding that we obtained, that the electric and magnetic field are collectively components of a anti-symmetric second-rank tensor. That means that under Lorentz boosts, the electric and magnetic field components will mix with each other. What is, for example, an electrostatic field in one reference frame will be some combination of electric and magnetic fields in the other. So they don't exist individually. They are observed as electric and or magnetic depending on the reference frame. Let's now check the equation of motion. So remember, mu alpha is just the form momentum p alpha. Now ds is c d tau, where d tau is the element of proper time. So the left-hand side of the equation of motion is just dp alpha by d tau. That's equal E over c f alpha beta u beta. D tau is equal to dt times the square root 1 minus v squared over c squared, or in a different notation, dt divided by gamma, where gamma is 1 over square root 1 minus v squared over c squared. The form momentum p has components E over c and three-dimensional momentum, and the forward velocity u with covariant indices, that's gamma c minus v. Now these are actually the same vectors. There's a proportionality m between them, but it's convenient to write them this way. So let's write the space-like part of the equation of motion. That's the one that comes from setting alpha to 1, 2, and 3. Let's start with alpha equal 1. So on the left we have d px by d tau. Now d tau is dt divided by gamma. So we can write dpx by dt, gamma goes in the numerator. Now E over C, and we need to multiply the row of the F matrix corresponding to alpha equal 1, that's the second row, by the column vector U. U has a common factor gamma that we can take outside, and then in the bracket we have EXC plus BZVY minus BYVZ. So here gamma cancels on the two sides, and the two terms involving the magnetic field give us the x component of the cross product of V cross B. So putting this all together, we can write dpx by dt equals E times EX plus E over C and the x component of V cross B. The equations coming from alpha equal 2 and 3 will give similar equations for the y and z components, so we can simply rewrite this in full vector form, and this is the familiar Lorentz force. We have only looked at the space-like components of the equation of motion. The time-like component is not independent. If we wrote it down, we would obtain dE by dt equals charge times E dot V. So this is a fairly obvious expression. The left-hand side is the rate of change of the energy. The right-hand side is the rate of work done by the Lorentz force. The magnetic field does not do work because this part of the Lorentz force is orthogonal to the velocity. It is quite obvious that the four components of the equation of motion are not independent, because we know that there is a equation that the contraction of P with itself is just m squared, which implies that d by d tau of P alpha must be equal to 0, or in other words, P alpha dP alpha by d tau is 0. Now, the right-hand side of the equation of motion is explicitly consistent with this constraint, because if you multiply the equation of motion by P alpha and do the contraction, the right-hand side will look like E over C, P sub alpha, F alpha beta, U beta. Now, P alpha is just M U alpha. So I can get rid of P and write M U alpha here. Now, the expression here is identically 0 because of the anti-symmetry of the tensor F alpha beta. So this is fully consistent with the left-hand side explicitly being equal to 0. This concludes this lecture, where we have figured out how the electromagnetic field appears in the relativistic theory, starting from a Lorentz invariant action and adding a term that represents the interaction of a particle with a field.